morning, or whatever. Um, we're going to talk about overlap and bonding, um, and just some of the ideas that all of this we talked about last year as well. We might go into a little more detail on it this year, but we're talking about the idea of what happens, what really truly happens when a covalent bond forms. Now there are different ideas, there are different models on how this occurs. We're going to focus mainly on one model because this is the model that the AP exam focuses on for now. Actually, in a year or two, supposedly they're going to go to, or at least they're going to discuss a different model as well. But the one that they really talk about now is the one that has to do with the VSEPR, valence shell electron pair repulsion. And so that's the one that we're going to deal with mainly. And orbital hybridization. So this is going to be familiar, but it's probably a little bit rusty in the back of your mind because we talked about this very briefly and then we went past it. But it's the idea of the different sp orbitals, and then we'll get into the idea of sigma and pi bonding and that sort of stuff. So we're going to cover this fairly quickly. Hopefully it comes back to you. Hopefully this makes sense. I've tried to put a lot of pictures in here because I think with this stuff pictures help. So the idea here is when we're talking about covalent bonds, we're talking about sharing of electrons, okay? And in order for electrons to be shared, what really has to happen is the orbitals that those electrons are in end up having to overlap in some way. Okay, so if you got two hydrogen atoms like this picture on the left here, they're one electron that each of them have. They're both in s orbitals, the 1s orbital. And so in order for them to share those two electrons to form H2, those two s orbitals have to overlap. Okay, and then the electrons can kind of go back and forth inside those overlapped orbitals, and those electrons are shared there. With an HCl, you've got an s orbital overlapping with one side of a p orbital. Okay, and that's where your overlap happens there in HCl. And then in Cl, or Cl2, then you're going to have two p orbitals overlapping one another, and that's how you end up with your Cl2 forming. Okay, and you can think about all of this in terms of where the valence electrons are that are going to be shared. The valence electrons in the chlorine, I mean the hydrogen only has one, so it's a 1s. 1 is its valence electron. The chlorine has quite a few valence electrons. It has 7. The ones that are going to be involved, I guess I should say the one that's going to be involved in bonding with a hydrogen is going to be its 2, or I guess I should say 3p orbitals. Okay, and so chlorine has 5 electrons in its 3p orbitals, and if you recall, there are 3 possible orientations for a p orbital: px, py, and pz. And pz is kind of going into the screen and coming out of it. Okay, so one of these orbitals, probably the px in this particular example, is going to overlap with the s orbital of the hydrogen, and that's what's going to get shared there. Okay, so hopefully that makes sense. It's just kind of thinking about how these orbitals work and how they overlap with one another. Okay, so we have to have overlap in order for this bonding to occur. Okay, and so we can sort of think about this as far as the way that the bond forms, and this is kind of an important concept. They might ask a question about this in the AP exam, but the idea here is there's this ideal distance between these nuclei, where the electrons are shared in just the right way, so that it minimizes the repulsion between the nuclei, and it maximizes the attraction. Okay, so if you look at this, there's just kind of a sweet spot right here. Okay, at 0.74 angstroms, which an angstrom is 1 × 10⁻10th meters, and there's this just ideal spot right here where the electrons that are being shared in the middle here are attracted to each of the nuclei, but the nuclei aren't so close together that they're pushing each other apart. Okay, And so you get any closer than that with the two atoms. Now this is not energetically favorable anymore. You have to put a lot of energy into it to get them to get any closer, because the protons in the nuclei don't want to be any closer together than 0.74 angstroms, because like charges repel. Okay, but then you get too far away, and again, that's not energetically favorable either, because the electrons are not sufficiently attracted to the nuclei. Okay, and then you get too far apart, and obviously they're not even bonded anymore. Okay, so there's kind of this ideal distance for a bond. Now, bonds do vibrate. They sort of they move out a little bit, and then they come back in, and they move out and come back in. So there is this movement that's happening here, but they're going to fluctuate around that ideal distance. That's basically what I was just saying. Okay, kind of a weird place to put this. I didn't know where else to put it, but this is just a strange question that I saw on an AP exam one time, so I wanted to include it here. And I don't think this one is on your packet for this time. But in the H2S molecule, the HSH bond is close to 90 degrees, and on the basis of this information, they want to know which atomic orbitals of the sulfur atom are involved in bonding with the hydrogen atoms. Okay, and so we're just thinking here about, and it may or may not be helpful to actually draw the Lewis structure for this, but usually that's a good idea to just get an idea of what we're dealing with here. We've got 8 valence electrons. We just used up 4 of them. The hydrogens are okay the way they are, so this is going to end up being the way this one is structured as far as the Lewis structure. So what they're asking basically here, if the HSH bond angle is about 90 degrees, then what orbitals are overlapping here? Okay, and so we got to think about sulfur. Sulfur is very similar to chlorine in that its outer electrons are going to be 3p in the 3p orbitals. Okay, and let's see, that sulfur actually has, let's see if we think about these orbitals here, we've got the px, the py, and the pz. Okay, and let's say that we've got 2 electrons already in the pz orbitals, and we've got 2 electrons in the py orbitals. Okay, so if we've got 90-degree bond angles here, yes, yeah, I knew the Lewis structure is going to mess this up a little bit. The idea here is these hydrogens, if they're sharing electrons with this sulfur, then it's going to look something like this. Okay. Now, I can't draw this very well in 2 dimensions, but you got to remember that these orbitals are actually forming sort of a tetrahedral type structure, but the lone pairs are pushing on those bonds to make the angles a little bit closer to 90 degrees. Okay. Yeah, I think the picture is probably more confusing than anything. But this is kind of the problem that we run into with these, is the idea that, well, why would these be 90-degree angles? And you can sort of get to the idea of 90-degree angles just by remembering, okay, the lone pairs are going to end up pushing on this HSH bond and bending it down. Okay, but when they're asking about which atomic orbitals of the s atom are involved in this bonding, really the main thing to remember there to probably answer that question, it's not so much about the 90 degrees. I would say it's a lot more about the orbital diagram for sulfur. Okay, maybe this will actually be less confusing. So in our valence electron energy level, we've got 3s electrons, and then we've got 3p electrons. Okay, and so the 3s orbitals are full, and the 3p, you've got 1, 2, 3, 4 electrons in sulfur. So there's 2 places here where the orbitals are unfilled. It just makes sense that the bonding here, if it bonds with hydrogen atoms, it's going to take place in the 3p orbitals. Okay, So I guess I wouldn't worry as much about the 90-degree thing. That may be information that's just going to be more confusing than anything. But when we think about a bond with a hydrogen atom, um, it just makes sense to think about the 3p orbitals being involved in that bonding. Okay, so hopefully that makes sense. Hopefully I didn't confuse you more. But I looked at this question as just kind of an awkward question. I wasn't sure where else to place it as far as the question that it was asking. Okay. All right. So now we need to talk about hybrid orbitals here. Here's the problem with the atomic orbitals the way that we know them. They're all different shapes. Okay, so we've got an s orbital, and we've got 3p orbitals here in most of our valence electron configurations. And thinking about that s and 3p's, really VSEPR, valence shell electron pair repulsion, only works if all the orbitals are exactly the same. And that's not true. Right, we have an s orbital here, and then we've got these 3p orbitals all turned in different orientations. So these aren't all the same shape, which really screws up the idea of valence shell electron pair repulsion, because we're assuming here, when we're getting these electrons as far away from each other as we can, we're assuming that everything's equal as far as the size and the shape of the orbitals. Okay, and so a lot of this is just trying to describe in reality what we're observing to be true, okay? Or describing, I guess, with models what we know to be true in reality. And what we know to be true is when we measure CH4, when we measure the bond angles and the bond lengths and everything like that on CH4, we know it's tetrahedral. It's 109.5 degree angles, okay? Everything's symmetrical. We know that because CH4 is nonpolar, okay? So what that means is all these orbitals must be somehow the same, okay? And so the idea here is, well, maybe these things hybridize. In other words, maybe they sort of mix, and the S's and the P's sort of blend a little bit. And then when we get into D's, then maybe even the D's blend a little bit to make these orbitals that are exactly the same, okay? So we've got something like beryllium. Okay, and beryllium in its ground electron state would not be able to form bonds because it has full orbitals here, 1s and 2s. Okay, its orbitals are already completely full. But if it does something called a promotion and expends a little bit of energy to put one of these electrons into its 2p orbitals, then it's going to be able to bond, because now it has two half-filled orbitals, and those can now share electrons with other orbitals that come in from other atoms. Okay? And so the idea there is a promotion. And then the theory is that once that promotion happens, the s and the p orbital that are both half full sort of hybridize, okay? And all that means is they blend so that now you have two orbitals that look exactly the same, okay? And so you've got these two orbitals that are equally shaped. And now what you can't see when they get put together is that, you know, you've got the small lobe right here from the one, and you've got the small lobe from the other. Let me see if I can trace that a little bit better so you can tell what belongs with what. So with this particular orbital right here, there's a small lobe on the other side of it, okay? And then with this other orbital over here, there's also a small lobe right here, okay? You put those two together, that's what happens when you combine these two. It's going to look like that. And because they're hybridized, that means that when we form something like BeF2, it's going to be completely linear. These things are exactly the same, so they can get completely on opposite sides of the beryllium, and you have a linear molecule there, 180 degree angles. Okay? And so the idea there, you've got these two hybridized orbitals around the beryllium, and now you can have your 180 degree angle here. You have a perfectly linear molecule, okay? Which we know it's linear because, again, there are electronegativity differences here, but overall this molecule is not polar, so it has to be symmetrical. Okay. So the orbital diagram for beryllium is going to look like this. You've got the 1s orbital, and then you've got two hybridized sp orbitals now. Okay, and those sp orbitals are going to look like that. And then you've got the empty 2p orbitals. They're not involved in the bonding, so they didn't have to hybridize. Okay, and again, this is just a theory of bonding. Scientists are not exactly sure if this is what is going on, but this is a model that's consistent with what we observe. Okay, so these sp hybridized orbitals, they're sort of in between as far as their energy. They're a little bit higher than the 1s, but they're a little bit lower than the 2p. Okay, now if we use boron here, okay, I should have your note sheet out so that I know exactly what you're looking at here. Sorry, hang on just 1 second, because I want to make sure that what I'm showing you is consistent with what you're seeing on your worksheet. Wrong place, sorry. Okay, so what you're seeing on your worksheet here okay, yeah, it looks like it's the same. So when we're using the model for boron here, same thing is basically going to happen. Except now we have 3 electrons instead of just 2. Okay? So we've got a full 2s and then 1 electron in the 2p orbitals. Okay? The promotion happens here. This electron in the 2s ends up in the 2p. And now we have 3 separate places where this boron can bond with something, form a covalent bond, share electrons. Okay? And so what it's going to do here is these s's and p's are now going to hybridize. They're sort of going to mix together, and we end up with sp2 hybridized orbitals. Okay, and the name of the orbitals, the name of the hybridization, just comes from the fact that there are 3 orbitals doing the hybridization there. 1 is an s, and 2 of them are p's. All right, and so we end up with sp2 hybridization here. And so again, the way that this looks, now you've got 3 orbitals that look exactly the same. Okay, and if you get those as far away from the central atom as you can, or far away from each other on the central atom as you can, then you end up with 120-degree angles, which again is consistent with what we see for BF3. Okay, if we're doing this with carbon, now we've got 4 electrons, so this 2s electron right here gets promoted. And now we've got 2s and 3 2p's, so that can hybridize into sp3. Okay, and now you've got 4 places where this thing can bond. Okay, and again, that's going to form a tetrahedral geometry, because when you get those as far away from each other on the central atom as you can, they're going to form 109.5-degree angles. Okay. Now, when we get to the expanded octets, then we've got to talk about d orbitals, okay? And so we've got something here like, let's see, what is this? 3s, 3p, and a 3d. So what's happening there is, you know, so this is something like, trying to figure out what this is. Something with an expanded octet. Sorry, hang on 1 second. Let me just figure out what this is. My brain's not working this morning. Okay, sorry about that. What you're looking at here, you're looking at something like a phosphorus atom. Okay, and the idea here, come on, get out of the way, here we go. The idea here is that you've got what you originally had, and this isn't really showing it. Oh yeah, it is down here, sorry. So what you originally had on this one is 2 in the 3s and 3 in the 3p's. So that's going to be a phosphorus atom, okay? And so when you have something like that, you still only have 3 places that you can bond unless this s electron can somehow get promoted, okay? And because it can't go to the p's, it's going to have to go into a d orbital in order to have, you know, the 5 places to bond. And then you blend all of those together and you end up with sp3d hybridization. Now what this explains is, it explains why anything in the second row and above can't do expanded octets, because you need to get down to the 3d orbitals before you actually have the ability to do this, okay? So that's why something like phosphorus or sulfur or anything below them on the periodic table can expand their octets, is because now they have these d orbitals available that they can promote an electron into in order to make these higher hybridizations, okay? So then you've got sp3d, and you've got 5 of those, so that means there's 5 places where you can bond with the central atom, okay? And that makes the trigonal bipyramidal geometry possible. Or, again, if you have something like sulfur, now you can do 6 orbitals around the central atom, each at 90 degrees, and now you've got an octahedral arrangement, okay? So the nice thing about this is, whether you completely understand all of what we just talked about, what you actually have to do with this on the AP exam is fairly straightforward and simple. And that is, you know, once you know the shape of the molecule, once you figure that out, the electron domain geometry, you can figure out the hybridization, okay? If you have a linear geometry, that means you've got an sp hybridization, okay? If you have 3 domains around the central atom, trigonal planar geometry, then that's sp2, okay? If you've got 4 domains around the central atom, then it's sp3. And then as long as you just remember how many orbitals there are available in each of the different shapes, like there's only 1 s orbital available, there are 3 p orbitals available, and then you've got to go into d's after that. Then you can remember, okay, if I have 5 domains around the central atom, then this is sp3d hybridization, and then if I have 6, it's sp3d2, okay? So that's basically how that works. So again, when we're actually figuring these out, this is not that difficult. If we want to indicate the hybridization here, we've got something like NH2, so, or NH2 minus. So we're dealing with 8 electrons here. We just used up 4 of them, so then the other ones will go here, okay? So for A here, all you have to do is count up the domains around the central atom. We have 4 domains around the central atom, which means that we've got 4 hybrid orbitals here, okay? Even though 2 of them are lone pairs, they're still all going to hybridize so that they can get as far away from each other as possible. And so what we end up with here is sp3 hybridization, because we've got 4 domains around the central atom, so that's going to be sp3. Okay. For letter B here, SF4. Let's figure this one out. So in this one we've got 28, 6, 34 electrons. And we just used up 8 of them around the central atom, so that leaves us with 26 electrons. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24. That leaves us with 2. So that ends up giving us 26. Just double check my math here. 28 plus 6 is 34. That's right. Minus 8 is 26. Okay, that's right. So we have 5 domains around the central atom here. And because we have 5 domains, then 1 of the S's, 3 of the P's, and 1 of the D's must have hybridized to get those as far away from each other as possible around the central atom. Okay, so we end up with sp3d hybridization. So hopefully that makes sense. It's not difficult. All you have to do is count the number of domains around the central atom, and you can figure out your hybridization from there. Okay, hybridization of the carbon atoms in a molecule of C2H4. All right, well, we'll assume here that we've got a structure that sort of looks like this, okay? The carbons are attached to one another, and the hydrogens, I'm sorry, the C2H4, not H2. So you've got the carbons attached to one another and 2 hydrogens on each carbon. And again, you don't have to make the shape look like this. You could put them straight up and down on the carbons. So we have used up, let's see, we've got 4, 8, 9, 10, 11, 12 electrons total. We've used up 2, 4, 6, 8, 10 of them. That leaves us with 2. So the best place to put the last 2 would be as a double bond in the middle. That's going to make both the carbons happy, okay? And so, again, we're just counting domains here, and these are both the same. Both these carbons are the same. There's only 3 domains around each of the carbons, because remember, the double bond counts as 1 domain. So if there's 3 domains, then we're talking about sp2 hybridization around both the carbons, okay? So again, you're just counting the number of domains around the central atom, just like we did yesterday, and that's going to lead you to the hybridization, okay? So this is part of a theory called valence bond theory, okay? And in valence bond theory, hybridization is a big deal. Now, valence bond theory does not explain everything that there is to explain about atoms. That's why there's other models out there. The molecular orbital bonding theory actually explains some things that valence bond theory doesn't. It's a little more complicated, so it hasn't ever been on the AP exam before. But in the next couple of years, they're going to start phasing that in as well. For right now, we're just talking about hybridization and how this works. Okay, so this is the valence bond theory. This is the one we're going to learn. And valence bond theory involves the sigma and the pi bonds, the idea of that, and explains some of the double and triple bonding that can happen between atoms as well. Okay, so the 2 ways that the orbitals can overlap, you can have sigma bonds, or you can have pi bonds, okay? Now, this is important. It's kind of easy to confuse sigma and pi and s and p orbitals, okay? You got to keep those ideas distinct from one another, all right? So s and p orbitals talk about the shape of the orbitals. The sigma and pi bonds, those are different things, okay? That has to do with whether we're doing a single bond or a double bond, okay? And so sigma bonds are head-to-head overlap, and those can happen between all these right here are examples of sigma bonds. Okay, so you get a sigma bond right here where 2 s orbitals are overlapping, but it's head-to-head overlap. Okay, which with s orbitals, that's the only way it can happen. But again, head-to-head overlap right here. They're directly overlapping. Okay, and then the same thing here. These are directly overlapping with one another. That's a sigma bond, okay? And hopefully you remember this from last year. The first bond that's formed is always a sigma bond, okay? That's a single bond. It's the first bond that always gets formed. Pi bonds are the second and third bonds that get formed, and so these are double and triple bonds, okay? And these are going to be side-to-side overlap, okay? So the idea here, and really, I'm not sure if this is my favorite picture of this because it's showing the overlap actually happening here. A lot of times you'll see the picture sort of like this. Okay, so they're side to side, and then what you end up with there is there's sort of an overlap in the areas there where the electrons can kind of go back and forth between these. But the idea is these are parallel or side-by-side orbitals, okay? They're not directly overlapping like the p orbitals were in the screen before it, okay? With the 2 chlorines. So you can see how those are turned to where you can just sort of push them together. But the pi bonds here, they're parallel to one another, okay? And pi bonds are always the second bond and the third bond that form. Okay, so you always have a sigma bond first, and then you're going to have pi bonds forming after that. Okay, so single bonds are always sigma bonds because, again, just as far as energy is concerned, sigma is a more favorable arrangement. So that's going to happen first. And then if other bonds need to form, if there are more electrons that need to be shared, then the pi bonds will form after that, okay? And so again, hopefully you remember this from last year, and what you have to do with this is relatively uncomplicated, okay? So you've got a single bond right here, that's a sigma bond, okay? If you've got a molecule like the C2H4 that we just drew a minute ago, there is a single bond in here, there's a sigma bond, and then the second bond that makes the double bond is actually a pi bond, okay? And then if you have a triple bond, you've got one sigma bond and two pi bonds, okay? So let's talk about how this works exactly. This picture, again, I know is a little bit confusing, okay? But what you've got here is you've got this CH4, or I'm sorry, CH2 here, and then it's double bonded to an oxygen on the other side. And this is just showing all the different orbitals, okay? So this carbon right here is sp3 hybridized. I'm sorry, sp2 hybridized, okay? And so that sp2 hybridization means that it's got a trigonal planar arrangement, okay? It's going to form 120-degree angles between all of its bonds, okay? So again, it just kind of, and now this isn't exactly right, because this double bond right here, there's more electrons there, so it's actually going to be pushing this direction, and that's going to make these a little bit greater than 120, and it's going to make this angle here a little bit less than 120, okay? But it's close to 120, and this is going to be a trigonal planar arrangement. There's a sigma bond here between the carbon and the hydrogen, sigma bond between the carbon and the hydrogen because you have direct overlap, and then there's also a sigma bond with the p orbitals here between the carbon and the oxygen, okay? And so those are your sigma bonds that get formed here. Now, what happens here, and you can kind of see this, there's a p orbital right here, okay? And then there's a p orbital right here on the oxygen. And then you end up with this region of overlap in between the two right here, okay? And this right here, this is the pi bond, the double bond, okay? So you've got the sigma bond forming in the middle, and then you've got the pi bond forming on the outside that makes up the double bond, okay? And that's kind of how that works when the carbon double bonds with the oxygen. Again, this is one theory of bonding, okay? And it's important to know that these p orbitals that overlap to form the pi bonds, they are unhybridized, okay? And so you've got these hybridized orbitals here, the sp2 hybridized orbitals, right here, right here. This is getting too messy. Let me erase some of this. Okay. So the hybridized orbitals right here, the one that's connected to this hydrogen, and then the one right here that's connected to this hydrogen, and then the one right here that's overlapping with the oxygen. That's the sp2 hybridization. Okay, this p orbital right here, it's unhybridized. Okay, and so it can form the double bond with the oxygen. Okay, and then in triple bonds, basically you've just got two different pi bonds happening there between parallel p orbitals, okay? So again, you have the hybridization on either end. This is just sp hybridization, because if you look at the way that this thing is drawn, acetylene is C2H2. So the Lewis structure is going to look like this, okay? So what you've got there is two domains around the central atoms. That's going to be sp hybridization, okay? This is an sp orbital. This is an sp orbital, okay? And this one right here, the two sp orbitals on the two carbons overlap and form a sigma bond, okay? And then you have two unhybridized p orbitals still, okay? And this one, the py, overlaps with the other py to form a pi bond here, okay? And again, just, you know, top and bottom, that's just one pi bond, okay? Even though it looks like two different areas where the electron can be, which it is two different areas, okay? But that's all still the same orbital, so when those orbitals overlap, that's just one pi bond, okay? And then the other one, again, this gets too messy and crowded here, But the other one is the one that's coming out from the screen and going back into the screen. The PZ orbital right here is overlapping with the PZ orbital here, okay? And so you end up with this second pi bond that forms, okay? So you have one S, or one sigma bond there and one pi, or two pi bonds. One sigma bond, two pi bonds forming there. And the hybridization is sp, okay? So a lot of things to kind of put together there, but the idea here, this is the Lewis structure, okay? The shape is linear, the hybridization is sp, and there's one sigma bond and two pi bonds formed here between the carbon atoms, okay? And that sort of describes everything that we need to describe there. So the Lewis structure for HCN, and then we want to describe how these bonds are formed in terms of overlaps between hybridized and unhybridized. Okay, so we've got HCN. First thing you always want to do on these is just draw the Lewis structure, okay? We've got a total of 10 valence electrons here. We just used up 4 of them. We've got 6 left. Hydrogen doesn't need any, so 1, 2, 3, 4, 5, 6. Well, that doesn't work out very well for the carbon, so probably what we're going to have to do is swing 2 of these pairs in from the nitrogen and make a triple bond between the carbon and the nitrogen, okay? And so again, what we want to think about here, this is sp hybridization, okay? And so that means between the carbon and the nitrogen, and really thinking of carbon as the central atom, okay? And I'm going to do a horrible job with this drawing here. But this carbon has one hybridized, or 2 hybridized orbitals here. Okay, they're both sp orbitals. And one of them is sigma bonded to a hydrogen, and the other one is sigma bonded to one of the nitrogen's p orbitals. So I've got my nitrogen over here. And again, I'm just very bad at drawing these things, okay? And so there's your overlap, there's your sigma bonds, okay? So we've got one sigma bond right here, and then we've got one sigma bond forming right here. Then, if you can just sort of imagine the other unhybridized p orbitals here on the nitrogen and the carbon, there's a pi bond that forms the double bond, and this is the part that I really can't draw in 2 dimensions, but you've got another p orbital that you have to imagine going into the screen and coming out of the screen. Okay, and then the same with the nitrogen, and those are overlapping to form your other pi bonds. Alright, so what we end up here with is a triple bond, okay? Here's your sigma bond, and here's your sigma bond. This is just, it gets messy when I try to draw these. And then your pi bonds are the ones between the parallel p orbitals. Okay? Hopefully that makes sense. Alright, now, this also helps to explain resonance. Alright, so now we're going to come to kind of a deeper understanding of resonance here, hopefully. And this is an NO3 1-, which is actually a question on your last test that I think I'm probably going to take off because I wasn't intending for it to be this difficult, especially before we talked about this. But the idea here is you've got 3 different possible resonance structures if you're drawing all the resonance structures for this. Okay, so if they ask you to draw all the possible resonance structures for NO3- on the AP exam, this is exactly how you draw it. Now this is not what's happening, okay? So let's see if we can kind of talk about what's happening here, okay? So each of these 4 atoms in the nitrate has a p orbital, okay? And what happens here is instead of having the double bond between, just one nitrogen and one oxygen and then a single bond between the other 2, what's really happening here is you end up with sort of this big delocalized region of overlap between all of them, okay? And so really the electron can kind of travel anywhere in that entire area. And that's why when we talk about the strength of the NO3, the bonds between the nitrogen and the oxygen, when we write this out to sort of try and show that, then what you end up with here putting in all the lone pairs and all that, but what you end up with here is bonds that are about 1 1/3, okay? Because the electrons spend about 1/3 of their time here, but they spend about 1/3 of their time here and 1/3 of their time here. I say here, but they could be in the lower lobes as well, okay? And so, I feel like I'm just circling stuff here. I hope this is making sense. So basically, that's the idea behind the resonance, that in reality, this is sort of an average of the bonds, just based on the amount of time that the electrons are spending in any one place, okay? And so we would refer to the strength of these bonds as 1 1/3. So they're going to be a little bit stronger than single bonds, but quite a bit weaker than double bonds, okay? And then as far as their bond length, they would be a little bit shorter than single bonds, but still quite a bit longer than a double bond, okay? And so that it's really the average there. So they're delocalized is what we would say. Okay, now this can happen with a benzene ring as well. And so if you notice here, when you've got this ring of carbons, okay, they're all connected by this sp3, these sp3 hybridized carbons. Okay, so you can kind of tell here, 1, 2, 3 hybrid orbitals around each of the carbons, okay, which actually leaves one empty p orbital, and that's what's being shown over here. Okay, each of these carbons has one empty p orbital, and they're all parallel to one another. They're all oriented in the same direction. And so what happens here is you end up with this planar ring, and then you end up with a resonance structure that looks sort of like this, where really the electrons are delocalized and they can sort of travel all throughout those p orbitals. And so you end up with something, instead of writing the alternating, that's a bad 6 reading, but instead of writing the alternating bonds like this, it's probably more correct to do something like what they wrote here, okay? It's just a circle showing that the electrons, the double bonds are kind of, they're in there, okay? And so you have, essentially what you have there is 6 extra electrons that are, covering the space of 6 bonds. Okay, so you have kind of a 1.5 bond on each of those carbons. It's actually a very stable arrangement. And you can actually see that because it's got, the carbons in one plane, kind of horizontal plane, and then it's got all of those connections between the p orbitals. So it's a very stable arrangement of a molecule. Okay, so to describe the delocalized pi bonding in the nitrate, whoops, that's not right. It's supposed to say in the carbonate ion, not the nitrate ion, because we already talked about the nitrate ion. So CO3 2 minus. All right, so when we draw the Lewis structure for CO3 2 minus, I'm sorry, I know this is getting long. Then what you've got here, you've got a total of 18, 22, 24 electrons. Okay, we just used up 6, so that leaves us with 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18. Well, we used up all 18, but the carbon's not happy, so we're going to have one double bond here between carbons and the oxygens. And again, there are 3 different resonance structures that we could draw here. We could make the double bond in any one of these carbon-oxygen bonds, okay? And so what's really happening here, again, you've got, because you've got 3 domains in the middle, you've got a trigonal planar geometry here, okay? So you've got something that looks like this. Or actually, I should probably just draw a single bond here for the moment, okay? And then what you've got, this is a planar arrangement, okay? And again, it's so hard to see this without drawing a good picture, and I'm not good at drawing good pictures. But you've got, if you can just imagine a planar molecule, it's completely flat, just like I've drawn it, okay? And then this carbon and each of the oxygens have p orbitals, unhybridized p orbitals coming out from each of the atoms, okay? So from the carbon atom, there's a p orbital coming out of the screen and going back into it. Same with the oxygen. there's a p orbital. Each of the oxygens, there's a p orbital coming out and going into the screen. And then you have this overlap basically between those p orbitals. So I guess I could kind of try to draw this. It's not going to look very good. Just imagine these are coming out of the screen and going back into them. So these are all parallel to one another. Okay, and again, it's just not doing it justice here, but you end up with this sort of overlap between all of them. See, I just can't do it in 2 dimensions. My drawing is bad. Maybe I'll just show you an actual computer simulated drawing of the CO32- in class. I'm trying to describe it with words. For some of you that's going to work. For some of you, you probably need to see a picture. But the idea here is you've got a trigonal planar, so 120-degree angles, it's in a plane. And then the unhybridized p orbitals that are coming out from the carbon and the oxygens, they all overlap, okay? Just like they did with the benzene ring, just like they did with the NO3 before it, okay? And so hopefully that makes sense. And I've never seen a question exactly like that on the AP exam, so I think you're probably okay as long as you know what the geometry of this is and what the hybridization is and how many sigma and pi bonds. So we could actually talk about that with the CO32-. Really, we've got a trigonal planar geometry here. That's going to be the shape of this thing because it has 3 domains around it. Okay, we're going to have sp2 hybridization around the carbon atom, and we're going to have essentially we have 3 sigma bonds here. What's that? There's a sigma. There's a sigma, and there's 1 sigma here. So 3 sigma bonds, and then we're going to have a total of 1 pi bond, even if it's delocalized around all of them. So we've got 1 pi bond there because of the double bond. Okay, as long as you know this, then you should be okay. All right. So that's it. Hopefully that makes sense. I know that's kind of complicated stuff, but again, we're just trying to make models that are consistent with what we observe experimentally. So that's where that comes from. And we won't talk anymore about the bonding theories or anything like that. That's about as deep as they get on the AP exam. Okay, see you next.